Right, hello everybody. So in this video, we're going to be taking a slow and methodical journey through the world of vector spaces. And the main intention of the video here is to really become familiar with the abstract concept of a vector space. So not to say that a vector space is one particular kind of vector space. So for instance, Euclidean 2 space or Euclidean 3 space and so on. But to really see from a bird's eye view what is the concept of a vector space. Okay, so here we have three different examples of vector spaces. And so the first one that's probably most familiar to everyone here is Euclidean n space, so n-dimensional Euclidean space. And what is it? So it is the set of all n vectors, that is all n tuples of numbers where each of the numbers are just real numbers. And then we define a specific way of adding two such vectors. And the way that we add these two such vectors is just given by this line over here. And we also equip this set together with a way of scalar multiplying such vectors. So that's what's given here. And the resulting thing that we get is called a vector space. And in particular, it's called Euclidean n space. And so this is just one example of a vector space. The next example here in the red box is here. So given an interval I, so I is just an interval, so for instance it could be something along the lines of 1 to 2, just all numbers strictly in between 1 and 2. And then we can define the set of all functions from this interval into the real numbers. And so this set really, it is an enormous set consisting of all possible functions from this interval into R. And then again, this set can be equipped with a way of adding to such functions and scalar multiplying them. So for example, if I take two functions here, so all of the functions I mentioned going forward are just going to be from the interval 1 to R. So given two such functions, how do I define the addition of two functions? Well, this is a function which, when I plug in x, I get a specific number, namely f of x plus g of x. And this is, of course, well defined. And so to any two such functions, I can define the sum of these functions. So in any case, this set here has an addition, which I've just defined. And so we can kind of think of that as a vector addition. And in a similar way, we can define the scalar multiplication. So given any function f, let's say again, so well, in fact, given any real number k, and any function, again, from the interval 1, 2 into R, I can scalar multiply this function. Now, how do I do that? What is k times f? Well, again, this is a function. And it's a function which, when I plug in a variable x, I get out k times f of x. And so what I've defined here, you can see, is quite similar to Euclidean space, because the only thing that's changed, really, is the set here. So instead of a set of n-dimensional Euclidean vectors, now I'm dealing with a set of all functions from I into R. And then also the way of adding them. So to the set, I can attach a method for adding these functions. And also I can attach a way of scalar multiplying them. And the resulting object is also going to be a vector space, and we'll get to the abstract concept soon. But the point is that the underlying sets here are really quite different. Here on the one hand, we're dealing with n-dimensional Euclidean vectors, and here we're dealing with entire functions from an interval into the real numbers. Okay, now similarly, we can talk about the set of all solutions to certain kinds of differential equations, linear homogeneous differential equations. And we can talk about their solution set. So imagine I give you a differential equation. In this case, y double prime plus y equals 0. And I ask for the set here, S, of all solutions to this differential equation. So for instance, sin x, you can check, is an element of the set. Sin x exists in the set. Why? Because if I take y double prime plus y, this is going to be negative sin x plus sin x, which is equal to 0. So in other words, sin x is a function, y. So if I define y is equal to sin x, then it's a function which satisfies this differential equation, and hence it's an element of the set. Okay, so I have a well-defined set here. And again, together with the same operations I defined over here, this will also turn out to be a vector space. And the reason for that goes back to some of the previous videos we have already seen about differential equations. The main property here is that if I take two solutions to a differential equation, let me say it in general. If I take any sequence of solutions of a differential equation, then any linear combination of those solutions will again be another solution. It's the superposition principle for linear homogeneous differential equations. So for this reason, this set, together with the same operations of addition and scalar multiplication, will form a vector space, and it's called the solution space to this differential equation. Okay, so let's take a look at the general definition of a vector space. So that's going to be given here. So what we saw in the previous examples is that a vector space always consists of a set, so a well-defined collection of things which we call vectors. But it's not just a set. It's a set together with additional structure, and that structure is given here in the gray box, particularly a vector addition and a scalar multiplication. Now, what does that mean, vector addition and scalar multiplication? Well, it just means that these two operations satisfy these two axioms over these 10 axioms over here. So the first one says that if I take two vectors in my vector space and I add them, I get another vector in my vector space. This is closure under addition. The next axiom says, well, if I take a vector and I scale and multiply it, then I should end up with a vector. The next axiom says just some of the behavior of the vector addition. So for instance, if I take x and y in my vector space, and then I add x to y, that should be the same as adding y to x. Another law here called associativity of addition is that if I take x plus y, and then I add that to z, it's going to be the same as taking x plus y plus z. And the rest of the behavior here you can pause the video and read, but it really says some of just the basic behavior that we want from a vector addition. So let's take a look at, for example, just a very simple example, which we've already seen, which is R2. So R2, this is really the most familiar of all vector spaces, all two-dimensional vectors. So what is this? Well, according to what we've seen already, this is the set of all pairs of numbers where the first and second components are just real numbers. Okay, so this is really the set of vectors we're dealing with here. Okay. Now, what is the addition on the set? Well, the addition, as we know, is if I take x, y, and I want to add that to, let's say, x prime, y prime, what do I have to end up with? I have to end up with another vector in my vector space. So if V is the set of all pairs of numbers, I have to end up with a pair of numbers. So from this pair of numbers and this pair of numbers, I want to produce now another pair of numbers. And the very natural way of doing this is taking x plus x prime and y plus y prime. And that's our vector addition. The scalar multiplication is quite similar. The way that we take a number, k, let's say, and scalar multiply a vector by that number is, again, we want our axiom 2 to hold. And so from this number and this vector, we need to produce another pair of, or another vector or another pair of numbers. And the way that we do that is very naturally again. We just take k times x and then k times y. So this is Euclidean 2 space, or really the Cartesian plane. And it's very straightforward to see that all of these axioms are going to hold here. So for example, let's actually prove that one of these axioms is going to hold. Well, first let's just observe that some of them are going to really easily hold. So for instance, this first axiom here, closure under addition, that's going to be quite straightforward to see. Why? Because if I take a pair of numbers, in other words, I take two vectors, x and y, and I add them, well, I get another pair of numbers. So I get the closure axiom. Okay, axiom 2 is very, very similar. If I take a number and I take a vector, in other words, a pair of numbers, and I scale and multiply, I get another pair of numbers. And so if I take a vector and a scalar and I scale and multiply, I get another vector. So these two closure axioms hold very, very easily. Okay, let's take the next axiom here. Let's see why this commutativity of addition holds. So for 3, for instance. Well, let's say I said x here was equal to, I'm going to now use vector notation, but again, this is just a symbol. I could write this, I could write something else. This is just a symbol to represent a certain pair of numbers, and in this case, this pair of numbers. So let's take this vector and this one here. Sorry, y1 and then y2. And let's check that the vector addition is commutative. Well, if I take x, so by the way, these represent really any two vectors in our vector space, right? So remember, our vector space is R2. So if I take x plus y, by definition here, this is just this. And this is just this. And then we can swap numbers around. So commutativity of just ordinary addition is true. X plus y. If x is if a is a number and b is a number, then a plus b is equal to b plus a, as we all know. So this is just going to be equal to this. And so we have this here. And now again, by the way I've defined the addition, which is given here, I can write this differently. I can write this as y1 comma y2 plus x1 comma x2. And this is just y plus x. And so what we've shown here is that if I take any two vectors, x and y, in my vector space, and I add them in this way, then it's the same as if I add them in this way. Okay, so that just shows you why this axiom 3 holds. No, it's very easy to check. You can check the rest of the axioms yourself, and they all will follow quite easily. Okay, so now let's take a look at a more complicated vector space. So what I want to show you next is that we can have vector spaces which really aren't as easy as the previous example. So for example, let's take a look at this vector space here. Well, we're going to show it's a vector space. Okay, so let's try to understand what's going on here. So first thing first, we have a specific set, C, and what is it? It consists of all pairs of numbers, x, y, where the y component is positive. So for instance, 1, 2 is in C, but let's say 0, -1 is not in C. You can think of this as really all points in the plane, which, well, the upper half of the plane, so where the y coordinate is positive. Okay, so that's what the set is. if I take the Cartesian plane, it's really everything that sits here above the plane. So all vectors which can be formed like pointing in upwards direction. Okay, so that's the collection of vectors that we're interested in. And then we're going to define vector addition and scalar multiplication in the following way, here. So x plus y, so x comma y plus x prime y prime is defined here. So this is really quite strange, right? If I take, let's say, 1, 2, and I want to add that to, let's say, 2, 3, how am I going to do that? What does this equal? Well, in this particular vector space, this is going to be, what do? I add the x components, just usually. So 1 plus 2, I get 3. And then I multiply the y components. So I take 2 times 3 and I get 6. So you can see here, this operation it's neither like multiplication, neither like addition. It's a combination of both. Okay. Now next, if I take a number, let's say k, and I scalar multiply that with this vector xy, what I multiply the first component x with k, and then I take y to the power of k. So for instance, if I want to take, in this vector space, I want to take 2 times 1, 2. Well, what is this equal to? Well, I take 2 times 1 and I get 2, and then I take 2 to the power of 2 and I get 4. Okay, so this is rather coincidental, but this is actually usual scalar multiplication in Euclidean space. But if you had to put 3 here, for instance, it would be different, right? It would be then 3 to the power of 2. So let's just point that out quickly. If I do this example, then I get here 2, and then I get here y, which is, in this case, 3, and k is 2. So I get y, 3 squared, which is 9. Okay. So that's how scalar multiplication and that's how the vector addition here works. And now let's check that this is in fact a vector space. So first things first, are these two operations the way that we've defined them? Is our vector space closed under these operations? Well, just by how they are defined, you can kind of see this. It's definitely closed under addition, because if I take any two vectors, let's say x and y, and I add them, what do I need to get? If I take, let's say, x comma y, and I add this to x prime comma y prime, what do I know? I know that both of these are vectors in this space here. So I should actually just say that we have both y and y prime are strictly positive numbers. Now when I add them, I get this vector x plus x prime, and then I get y times y prime. But since y and y prime are strictly positive, when I multiply them, I get a strictly positive number. So y and y prime being strictly positive will tell us that y times y prime is strictly positive. And in other words, what do we get? We get that this vector here is in fact an element of our vector space. Okay, so that's closure under the addition. All right, let's see why this vector space is, well, why this structure here satisfies the second axiom here, the closure under scalar multiplication. Okay, so I take an abstract vector here, x, let's say, and I scalar multiply it with a number. So I take here any number k, and I scalar multiply this with any vector here. Now the only thing I need to keep in mind is that y is strictly positive. Then I know just by definition that this is k times x, and this here is y times k. Now again, a similar kind of reasoning. Since y is positive, no matter what number you take, if you raise y to the power of k, you're going to get another positive number. And for this reason, you're going to get that this vector we've just defined this here is going to be an element of our vector space. And so that shows you that given any vector x and any real number k, when you scale and multiply, you get another vector in this vector space. Okay, so the closure axioms are valid. Now let's check the commutativity here of addition. So we take two vectors. So we take here, let's say, x and y, and we add this in this particular way to this vector x and the y prime. Again, we keep in mind that just because these are elements of a vector space, of our set C, these are going to be strictly positive numbers. And the way that we add here is that, I forgot about a prime here. So the way that we add is we just add the first components as usual. So we get this. And now what we do, we multiply. So we take y times y prime. And again, similar to as we saw in just two-dimensional Euclidean space, this is equal to x prime plus x, and then y prime times y. And by definition, this is just x prime comma y prime plus x comma y. Right, so what have we shown? We've shown that our vector addition here, it doesn't matter which order we operate. The vector addition is commutative, in other words. So that gives us this commutativity of vector addition. Now look, in a very similar way, the associativity of vector addition is going to be valid. And so I'm actually just going to leave this to you for you to check that associativity is true. Okay, now we get to the first kind of interesting axiom. This is the additive identity axiom. So firstly, let's try and understand what it's saying. This is saying that in any vector space, there is a zero vector. Okay, in any vector space, there is this particular vector, 0, which we call 0, and it has a particular property. And that property is that if I add it to any other vector, I get back that same vector. So going back to Euclidean space, if we take, for instance, just regular old Euclidean space, if I'm in R2, for example. Okay, now if I take any vector, let's say x, and it's equal to xy. Now just keep in mind, this, I'm now doing something separate from what was being done up here. So I'm back in Euclidean space. Let's try and ask ourselves, what is the zero vector there? Well, the zero vector is quite obviously just going to be this vector. And the reason for that is because if I take x, no matter what it is, and I add it to this vector 0, I get x comma y plus 0 comma 0. And in Euclidean space, this is when we add in the usual way. We just get x plus 0, y plus 0, and this is just equal to x comma y, which is equal to x. And so this law here, this additive law here, is going to be true. X plus 0 is equal to x. In general, let's just keep note of that. Let's go back to where we were in the very, very beginning. In general, let's try and just identify what is the zero vector in Euclidean space. So I'll just point out here that 0 is equal to this vector. So how many zeros are there? Well, there are going to be n zeros. And it will, for the same reason that we saw in Euclidean 2 space, this will satisfy the additive identity law. Okay, now what about here? What is the zero vector in this space over here? Well, I will just point out that the zero vector here, let's give it a different color. Zero vector in this space is just going to be, what is it? It's going to be a function, right? So this is going to be an element of the set, but a very particular one. And namely, it's going to be a function that when I plug in x, remember, everything, whenever I refer to elements of the set, it means it's going to be a function from I into R. So 0 in this particular case, it's a function, but it's a function that when I plug in x, I just get back 0. So no matter what x I put into the function, I get 0. And then you can check that this will be the 0 vector there. Okay, let's go back. So in this obscure vector space which we're looking at here, we want to know what is the 0 vector. What particular vector in C behaves like this? So let's try and just understand that the problem is not a trivial problem, right? Because, well, I mean, it is to some people, it is to not to others. But just to see why this is not going to be simply 0, 0, well, first reason is that 0, 0 is not even an element of C. And the reason for that is because, of course, 0 is not bigger than 0, strictly bigger than 0. So it means it's definitely going to be something else. Now, what something else is the question. So here I'm going to say, if we take x and we take x here, let's say x is again equal to x, y, and this is an element of C. In other words, this just means that y here is bigger than 0. Now, if we take this x, how should we define the 0 vector in our space? 0 vector, it's going to be a pair of numbers, and in the first component, we're just going to put the number 0. So this is the ordinary real number 0. And then in the second component, we have to put something strictly bigger than 0, and we're going to put 1. And let's see, if this works. So I'm just going to give the 0 vector a hat here, just to distinguish it from the ordinary number 0. So let's see here. This is definitely an element of C. So let's now check if this is actually the 0 vector. If I take x and I add this to 0, again, this is x comma y plus 0 comma 1. And according to how we've defined this addition over here, this is just you add the first components as usual, and then you multiply the second components. And here you can see everything is going to work out. We just left with x here and y, and this is just x. So this gives you a nice example of where the 0 vector is not, it's not like the Euclidean 0 vector or something very immediately obvious. And it just shows you that for vector spaces, things don't need to be very familiar. Okay, so we have this law that x plus 0 is equal to x. And this is, of course, true for any possible vector we choose in C. And so what we've actually just shown here is that this additive identity law holds, which is good. All right, now let's look at the next law. So the next law is all about additive inverses. So in Euclidean space, that's sort of the primordial example of a vector space. What is the negative of a vector? Well, let's say I give you a vector. So here is my vector, x. So this is x here, and it's the vector xy. Well, the additive inverse, so this is all in R2, by the way. Again, let's be careful. We're not dealing with this vector space C here. We're dealing with, again, Euclidean 2 space. And so here, in Euclidean 2 space, what is the negative of this vector? So what is the additive inverse of our vector? Well, it's actually just going to be the vector which points exactly in the opposite direction and has the same magnitude. In other words, negative x is, of course, it's going to be obvious when I say it's just negative x here and negative y here. And again, just to show you why, it's because if I take x and I add that to negative x, I get x comma y plus negative x comma negative y. and this is x plus negative x, which is x minus x, and then y plus negative y, which is y minus y, and this is just 0, 0, which is, in Euclidean space, the 0 vector. And so, because our vector x was really anything, x and y can be anything here, this law that x plus negative x is equal to 0 holds in general, so that in Euclidean 2 space, we've just verified the axiom 6. Okay, so now back to the main problem here. What about in our vector space C? What is the vector, the 0 vector in C here? Okay, so let's say we're dealing with this vector x, and it's equal to xy. And we keep in mind this is an element of C, which is again to say that y is strictly positive. And here let's try to discover what is the negative of x. Well, we have to define it. So negative x, we need to define it. Now, you're probably already catching on here that because I'm dealing with regular old addition in the first component here, that a good choice would be to put negative x here. Now, what about the fact that in the second component, we're dealing with multiplication? Now, because we're dealing with multiplication in the second component, you'll see that a good candidate here is to put 1 over y. And why is this in C? Why is this well defined? Again, because if we have that y is strictly positive, that will tell us that if I take 1 over y, it's also going to be strictly positive. Whatever positive number you take, no matter how small, if you invert it, you're going to get a positive number. So that this is a vector in our set C, an element of our set C, I should say. And so let's add them and check that we get what we want. Here we'll have x plus negative x equals the 0 vector. Sorry, not 0 vector, let's calculate that. So it's going to be x comma y plus negative x, which is negative x 1 over y. Again, according to how we have defined the addition, so I'll just try and keep this here. 1 second. So according to how we've defined the addition, which is given again, it's given here. This quantity here is going to be x plus negative x, which is x minus x, and then y times 1 over y. And so this here is just 0, comma 1. And by what we've just seen, this is actually the 0 vector in our vector space. So it's true. It's true. The additive law for this particular set also holds. If I add x to negative x and I define negative x like this, then I get that the additive inverse law holds. Okay, good. Now, what about scalar multiplication? How will this work? Let's check. Does 1 times x equal x? Okay, let's check. If I take, okay, let me first do some cleaning here. If I take a general vector, so I define x here again, x comma y, and now we know y is strictly positive. And then I take 1 times x. Well, this is just going to be, 1 times x comma y. And now we're referring to this second second identity here, that this is exactly equal to 1 times x and then y to the power of 1. And maybe not surprisingly, this is x and y, and this is just equal to x. So that this law for scalar multiplication holds, which is good. All right, now, because this video is getting quite long, let's actually just do the next axiom here, 8, and then maybe you can check for yourself if the remaining 2 hold. Okay, so distributivity of scalar multiplication. So we're given a scalar. So we take a general scalar, general number r, and then we take two vectors. Let's say x here is equal to x1, y1, and y here is equal to x2, y2. Now let's compute what is the left-hand side, the left-hand side over here. So this is going to be k, so the left-hand side of 8 is, in this specific case, for these specific vectors, it's going to be exactly equal to k times, so I'll just write it out, k times x plus y. And now we can unravel the definition here. This is going to be k times x1, y1 plus x2, y2. Now we can refer back to this law over here and see that this is exactly equal to k x1 plus x2 and then y1 times y2. Okay. Now we refer to the next law here, the scalar multiplication. And we can check here that this is just k times, so this is the usual times now, k times x1 plus x2. And then here we have y1 times y2 to the power of k. So we have this. Okay, good. So let's continue here. And you'll see that now I can use just the usual laws of addition, multiplication, and exponentiation. And I get k times x1 plus k times x2. And then here I get y1 to the power of k times y2 to the power of k. And now it's quite interesting because let's say that this was the first component x here, and this was the second component, second term, x prime. This was here the y, and this was the y prime. Then I'm sure you can see that this will just be exactly equal to k x1 y1 to the power of k plus, using this law here, just rewriting this expression using this law, is exactly, and then I put here plus k x2, and here I get y2 to the power of k. Now again, I can simplify this to say that this is just k times x1 y1 plus k times x2 comma y2. And again, how did I? So from here to here, I used the first this first definition here. Then from here to here, I used this over here. And so I can go one step further and just say what this is. This is just k times x plus k times y. And so that's exactly what the right-hand side is, as you can see here. And so what we've just shown is that this particular way of defining scalar multiplication up here is exactly, well, it distributes over the vector addition according to this axiomates. And so in other words, this particular addition and scalar multiplication satisfy the distributivity of scalar multiplication over vector addition. Right, now everything else follows very similarly. So why not leave these two axioms to you, and you can go ahead and verify it, or maybe not verify it and show that in fact this wasn't a vector space, and that the whole premise of the last 20 minutes is in fact wrong, but it will work out. So these two axioms here will hold, and I'll leave it to you to verify that. Okay, so let's just go back a second. Let's go back to the vector space axioms. So here are the vector space axioms. Now, these vector space axioms, as we've been talking about, they really describe the minimal behavior of a vector space. So any set together with any addition and scalar multiplication which satisfy these axioms is called a vector space. It is a particular example of a vector space. But this is a general list of conditions, a general set of axioms. And it's going to have some general consequences. And so those consequences, so this is really one of the remarkable things about abstract mathematics, is that we're going to make general conclusions, and those general conclusions are going to hold in every vector space. Now, in the beginning, it's going to be very easy, very simple kinds of general consequences. But, you know, when you build a structure, a building, you start at the ground level, but eventually you can get 300-400 meters off the ground. And the same in mathematics is true. Eventually, after enough theorem proving, one can get to some genuinely powerful results. So, let's take a look at just some of the simple consequences of these axioms. So, one of the first ones I want to show you is what we could call a theorem, and that is that in any vector space, there is only one zero vector. Now, if we just quickly zip back to this vector space axioms, the axiom 5 here, the additive identity, tells you that there is a zero vector, but there could be many. Why not? There could be 5 zero vectors, or 10, or 1,000,000. It doesn't tell you that the zero vector is the only one. But it will turn out that as a consequence of these axioms, there is in fact only one zero vector. So let's just see how that would work. So to any theorem, we should give a proof. And let's try and structure a proof of this fact here. So in any vector space, let's make everything clear here. So let's say let V be any vector space. Okay, because we want to prove something about about all vector spaces, and so we need to make that part of our statement. So we need to suppose let V be any vector space. Okay, now we want to show that there's only one zero vector. Now, how could we know that there is at least one vector, zero vector? But how do we show that there's only one zero vector? Well, let us suppose that let's say Z1 and let's say Z1 in V and Z2 in V are zero vectors. Okay. Now, what do I mean by they're zero vectors? Well, if I just go back to the axioms, it just means that if I take X, for example, so the axiom 6 here, if I take any X, no, not axiom 6, axiom 5, sorry. If I take any X here, and I add it to the zero vector, I should get back the X. In other words, if I take X plus, in our vector space V here, if I take X plus Z1, I should get back X for any possible X. If I take X plus Z2, I should get back X also for any possible X. Okay, so that's what it means to be zero vectors. But if these are zero vectors, then we have following very, very simple argument that if I take Z1 and I add it to Z2, then this will be equal to Z2. And why is that? Well, because this equality is just coming from, as what we said, Z1 is a zero vector. And at the same time, this here will be equal to Z1. And this is just coming from the fact that Z2 is a zero vector. And so that's very good. what we've just shown is that if I suppose that there are two zero vectors, then they're equal. So that, in fact, there is only one zero vector. So there is a unique, in other words, only one zero vector. In any vector space. And in this case, we say V because we're working in V throughout. Okay, good. So this is just one of the sort of elementary consequences of the vector space axioms. Let's take a look at just one more. It's going to follow along similar kinds of lines. So here we're dealing with the next theorem. So given any vector x in any vector space, why could it not be that this vector has two different kinds of inverses? So for instance, if we just take, this might be straightforward in R2 or R3, but if we go back to our, let's just take a look back at this vector space we were looking at earlier. Over here. If we go back to this vector space, you can see that the way that this vector space has been defined, it wasn't immediately obvious that the axioms would hold, and nor was it obvious what the zero vector was. And so, the intuition that Euclidean space has, that we really are just dealing with arrows, and that the way that we add arrows is we take the tail of one arrow and add it and shift it to the head of the other. That intuition will break down here. And for this reason, it's not so obvious questions like, for instance, does every vector in this vector space have a unique inverse? Is there only one such x, negative x in this vector space? Or could we have two? Could we have x and let's say I, different from this, which satisfies the same property? And the answer is no. And the way that's what this theorem is saying here. And so we're going to prove that. So let's give this theorem here a very short proof. Again, we want to say something about all vector spaces. So let's say let V be any vector space. And let x be any vector. In fact, let's just use normal x. So let x be any vector. And let's suppose also that we have two inverses for this element, vector x. So in other words, if I have two vectors, which I'm going to say, let's say y1 and y2, and these are inverses, additive inverses. For x. Now what does it mean to be additive inverses? It just means that if I take x plus y, I get 0. And similarly, if I take x plus y2, I get 0. Okay, so that's what I really mean by being an additive inverse, is that just these two conditions hold. Yeah, it's additive inverse because I'm adding and I'm getting 0. Now from this, how could I get that that y1 is equal to y2? Really, that's our objective. We have two inverses, and we want to show that they should be equal. That would then show that in any in this vector space, the inverses of x are, there's only one inverse to any element in x, any element in a vector space. Okay, so let's prove this. If I take here x, if I take y1 plus x, and I take x plus y2, let's see what happens here. Firstly, as we've noticed that x plus y2 is equal to 0. So this here is just equal to y1 plus 0. And then because 0 is the 0 vector, I just get that this is equal to y1. But I could have used the associativity law. So now I get y1 plus x plus y2. And now here, let's just be completely clear here. Here I can use commutativity. So I get x plus y1 plus y2. And again, now I can use the fact that y1 is an additive inverse of x. And so here I just get 0 plus y2. And this is just equal to y2. And so I get through these chain of equalities, which I should have written a lot neater. But in any case, the conclusion will be the same. I get that y1 is equal to y2. So that x has a unique inverse. Additively. All right, so these two facts are just very small consequences of the axioms of vector space. If it's needed, we'll show some more of these consequences in the next video and the next topic. But for now, this is the end. So thank you, and I'll see you next time.